Hey guys, welcome back to AlgoYogi. We are doing graph series, and next problem in the list is graph valid tree. So this problem is a premium problem on LeetCode. So that means we don't have access to it if you're not you don't have the subscription of LeetCode. So I just found this alternative code called LeetCode. This is where we will be solving this problem. So I'm not going to run the solution, so I'll be writing the solution, but I think we'll have to depend on just dry runs, because I don't have an account here, and I think you need like a WeChat to create the account. So given n nodes labeled from 0 to n-1 and a list of undirected edges, each edge is a pair of nodes. Write a function to check whether these edges make a valid tree. What's a valid tree? Well, the core difference between tree and graph is this cycle detection. Not detection, it's like presence of cycles. Cycles are allowed in graphs, but cycles aren't allowed in trees. So if you're calling like this structure, non-linear structure of nodes and edges, you can only call it a valid tree if you don't detect a cycle in it. It's a graph, of course it's a graph, but it's not a valid tree if there is a cycle, but it's a graph. We have to basically detect, given the number of nodes and edges, we have to basically find out if there is a presence of cycle. If there is a cycle, then we're going to return false. If there is not a cycle, then we're going to return true. The similar problem we have already done. If you have done these problems, course schedule 1, course schedule 2, find eventual safe state, these are going to have basically, they have the same concept, basically detecting cycle and then checking if you can visit all the nodes. So that's the same thing we'll be doing here. We'll be visiting all the nodes, and we'll be checking that while visiting any node, is there a cycle present at that particular node. If there is, then we'll be basically returning false if there is a cycle. So let's understand how we're going to solve it. So I've taken the first example right here. We are given 5 nodes right here. Then we have basically these edges. By the way, these are undirected edges. So that means if 0 is neighbor of 1, then 1 is also neighbor of 0. So these edges don't have any directions. So what we'll be doing is we're going to visit each node, and then while visiting that node, we will be checking the presence of a cycle. How do you do it? We're gonna run a DFS. That means like you're gonna visit a node, and before you mark this fully visited, temporarily you'll be marking it like visited false, and then you're gonna try to visit all its neighbors, and basically those neighbors, before you come back to your parent node, you have to check like if those nodes could be visited fully, so that there is no cycle. Right now in this example, let's say how are we going to visit? So first thing, we'll be creating the graph adjacency list. So I'm gonna call it like graph, and we'll be creating basically, so 0, 1, 2, 3, 4 and 5. Sorry, 5 is not there, just 4. So next to these, all these nodes, we're gonna basically put their parents. So we're gonna go through all these edges. So 0, 1, that means 0's neighbor is, I'm creating the neighbors list right here. So 1 is 0's neighbor, 0 is 1's neighbor, 0 has the neighbor 2, 2 has 0 as neighbor, then 3 has 0 as neighbor, then 0 also has 3 as neighbor, then 4 has neighbor 1, and 1 has neighbor 4. This is it. This is the adjacency list or graph we have created right here. Now using this list, basically we'll be able to traverse all the neighbor nodes of a particular node. So let's say we're going to start visiting all these nodes. So first, let's say, and then we'll be having something called, so there are like a couple of ways of solving these kind of problems. I like to do it a little differently. I like to have a map called graph map or something, or node map or node state. So initially, like before I start visiting it, I mark it false, saying that okay, I'm currently visiting it. So if I am basically, if any of the neighbor try to visit this node, that means that node that I was visiting, it's kind of in a loop. So there is a loop that circles back. So one of the neighbors of currently being visited node also pointed back to this. So that means you are stuck in a cycle. That's what we are trying to detect. So we have done similar problems, and I guess you would know what I mean when I say like this graph map. So let's say I'm going to call it node state map. Node state. So this will be a map, and I'm going to start visiting basically from 0 to n minus 1. So let's say first node is 0. By the way, this time when we start our visit, we also want to keep track of the parent node, and the reason is the parent node basically will tell us that that if I'm visiting 0, and then because in order to fully visit 0, I'll have to visit all its neighbors, and let's say while visiting 1, then I would have to skip its parent as a neighbor, because this right here is where parent is the one that's called 1. Parent means 0 called 1. I don't want to call again 0, because this is not a cycle. It's just there is a parent child parent relationship, and it's an undirected graph. That's why we have to keep track of this undirected edge. So I'm going to start exploring 0's first neighbor. By the way, because it's currently being visited, so I'm going to say 0 as false. It has the state false. Then I will visit 1. I'm trying to visit 1, so 1 will be marked false. Then you can also do this using visited set as well. Same thing. Then I will be exploring all the neighbors of 1, which is 4. Then while visiting 4, I will mark 4 as false, and then I'll try to explore all the neighbors of 4. Well, 4 does not have any neighbors, so that is why I'll be changing this state. State to true. Now this is marked true. Remember, 4 has a neighbor 1, but because 1 is parent of 4, then I will not try to explore that. Then I will mark this visited, come back to 1. 1 doesn't have any more neighbors, so I'll change its node state to true, because that means it has been fully visited. Then come back to 0. Let's explore 0's second neighbor, which is 3. Mark 3 as false in the beginning. That means you are currently visiting it. Let's try to explore all the neighbors of 3. 3 does not have any neighbors, so that means we can fully visit it. It's fully visited. We'll mark this true. Then what's going to happen? It will come back to the parent, which is 0. Then 0, okay. When I'm saying it doesn't have any neighbors, look, 3 has neighbor 0, but because it's a parent neighbor, so we're not trying to make like a cycle here, get stuck in the loop. So this is also visited. Come back to 0, then start exploring the last remaining neighbor of 0, which is 2. Mark 2 as false, like it's being visited. Then there are no neighbors of 2 except its parent, which we are not trying to explore, so we'll change this state to true. That means it can be visited, it's fully visited, so we'll mark this fully visited, and then we'll come back to the parent 0, and then we'll mark this also solved. Now while doing this, we did not get stuck in any cycle, right? We were able to fully visit all the nodes without getting stuck in the cycle. But there is actually a possibility, like if, let's say, if we change, so this one will actually return true, but then there is a possibility, what if 4 has a neighbor 3, and there was edge present here. So this edge means 3 and 4, they're also neighbors. So I'm making a change to this example. So here you can see, while I'll come over to 4, while visiting this, I will try to explore its neighbor as 3. Then 3 will try to explore its neighbor, which is like 4 is its parent, so it's not going to try to explore back 4, but it's going to try to explore 0. And then 0 will start its own cycle again. So we will get stuck in this cycle. So if you see right here, this cycle we will get stuck. That is why this will not be a valid tree anymore. Now we'll do the same thing. We'll perform the DFS on each node and then check the presence of a cycle. If there will be a cycle, then what will happen is, while visiting all of these will be marked false, and none of these could be marked true right here, and then we will basically return false in the end, because when it will try to access 0, and 0 will be marked false here because it's being visited, then it will return false, and then our entire code should return false. So let's write this. It will be of time complexity v plus e, which is like vertex and edges. It's going to be a simple solution. So let's write it down. So as I said, and then finally we can just return that DFS never returned false. And also our node state is basically the node that you have visited in your node state. They are same as, the number is same as the node that we're trying to visit. That means we could visit all the nodes, never found any state as false, and DFS returns true. So let's write it. You'll see how easy it becomes. So first thing, we'll be having our node state, but before we have our node state, or you can have node state. Node state is a map. Then we're going to have graph. Graph is also going to be a map, and in here we'll have each node and then its parents for node in range n. That's it. Now let's fill this. So for A and B in edges, we're gonna append that to my graph. So I'll say graph A. So A's parent, so A's neighbors are all the B's values. So graph at A, append B, and we'll do the vice versa because B is also neighbor of A, or I mean A is also neighbor of B, right? So that's done now. Then we are going to basically visit all the nodes and check if we can visit all these nodes without getting stuck in the cycle. Node state is very important here to check that cycle. So what I'll do is I'll have this for loop. So for node in, we don't have to say range. We can just say for node in, in range n. So we'll be going from 0 to n minus 1. So now here what we can do is call DFS on each node. Or instead of that, because this entire graph would be connected. So tree is not supposed to have like independent node, otherwise it will be invalid. So rather than having basically a for loop trying to visit all the nodes, what we can do is we can just simply return DFS on 0th node and then -1 as its parent. All right, then we also gonna check if we have visited all the nodes. This is the reason we are basically going to check that there are no nodes independent. Basically, it's not a disconnected graph. For this graph to be a valid tree, it has to be all connected and no cycle graph. So this length needs to be equals to n. All right. Then finally we can just write our DFS, because that's what we have called. So we'll do DFS, and this DFS will take the current node, and then its parent. I'm initially sending -1 as parent because 0 doesn't have any parents, right? Then what I can do is if this node already in my node state, it's already in my node state, then I can return that value. These will be true false values, so we are returning a valid value here. So node state at node, and here we're gonna have temporary value stored for this node. I'll be marking it because it's being visited, so I'll mark this as false. And the reason I'm marking it as false, so that let's say when I'm exploring all the neighbors of basically in graph, all the neighbors of this particular node, given that I'm skipping, if neighbor is equals to parent, I want to skip it. I want to continue, given that I've skipped all the this parent. But I want to check, like, if this neighbor, I'm gonna run DFS on it. So if DFS is false, not DFS on this neighbor, if this is false, that means it was being visited. It was being visited, and here it tried to basically access its parent. I mean, like, there was some other node that was connected to like some ancestral node, like, so that means it was creating a cycle. And this is the only reason I want to have this as marked false. So if any of the neighbor tries to basically explore it as its neighbors or children, you can say, then it will become a cycle. So if this returns false, then I will return false here. I will return false here. Otherwise what I can do is, that means I have explored all the neighbors, not the parent connection, but all the neighbors I have explored, and I never really basically got stuck in the cycle. That means I never try to access that particular neighbor or node where I already called DFS from. I hope that makes sense. Then what I can do is I can mark this true, because I have explored all its neighbors right here, all its neighbors without getting stuck in the cycle. That means I can mark this as true now. I can mark this as true, and then I will, oh my god, what is this? And then I can return true or this value, like, it doesn't matter. So both are true, okay? You can return this value. So in the end, I guess this will be it. This is the entire code. This is the entire code, and then we can go over this again. We have the node state. We are using to basically track what nodes are being visited, and while they are being visited, we keep a track of their state, that they have not been fully visited. That means we're marking them as false. Exploring all the neighbors. While exploring all the neighbors, there might be a case where we try to explore that node as one of the neighbors, and then we found that it's false, we cannot visit it. So it will be it will be returned from here. It will be returned as false from here, and then that will be it. So I guess this will be it. We'll not be testing it, although I wish we could test it. I wish we could test it, but then we'll have to log in, and I really don't want to sign up with my number here. Yeah, I mean, this cannot be submitted until you have this WeChat account. So I guess I'll be leaving it here, really, and hoping that it's correct. And then I think it's 100% correct. So, all right, I'll see you guys later. I'll mark this solved. I'll mark this problem solved. And remember that, like, instead of this state that I have, you can also have a visited set here. You don't have to have this one. You can have visited set here. If this node is in visited set, then you can return basically false. This could be returned false. So if you want me to make these changes, I can definitely make. And this node, this can simply be changed into visited set. This is doing the work of visited set. I just like the the accuracy that like it's not fully visited, so I'm marking it false, but I'm visiting it. So once I come out of like visiting all its neighbors, then I mark this as truly fully visited. Well, the same thing is done by visited set as well. So all right, then see you guys later, I guess. Yeah, it's a shame that like LeetCode has all these problems as marked like premium. Like, who, dude, you're not making these problems like yourself. Whoever like made LeetCode, you're not making it yourself. Like, these are the problems, real problems asked. This would be free to practice. But anyway, that's their idea. It's a great idea, and they're making money out of it. It's not philanthropic institutions, so whatsoever. I don't know, I'm just babbling here. Okay, I'm gonna stop.